So today we are officially starting electricity. I know y'all had Ohm's law yesterday, which deals with electricity, but today is just kind of the foundation, some of the basics about electricity. So what is electricity? Electricity is the flow of electrical power or charge. Basically, it's, pardon me, the flow of electrons. Now, not that we need to know this for any type of an assessment, but electricity is a secondary force of secondary energy source. We use something else to generate electricity. I can't just go out and scoop up electricity like I can coal or natural gas. So we have to use hydropower, geothermal power, solar power, something else to generate electricity. But electricity is the flow of power or the flow of charge. Generally, we think of it as the flow of electrons, because that is really and truly what is moving when we talk about electric circuits and electric current, is the electrons are moving. The protons are staying still inside the nuclei. So an electric charge is a property that causes a subatomic particle, such as protons and electrons, to attract or repel each other. Type or talk, does anybody happen to remember what charge protons have? Type or talk, what is the charge that protons have? Woohoo. Well, I got Autumn's alive. Is there anybody else that's alive? Uh-oh, where'd it go? So protons have a positive charge. Somebody besides Autumn. Oh, there we go. Now we got some more folks. What charge do electrons have? Again, just seeing what you remember from physical science. Yay. Oh, there we go. More folks are alive. So electrons are negative. So when we're talking about electrical energy associated with flowing charges, we're talking about a negative charge that is literally flowing throughout something. So if you look at a battery, for example, there is chemicals in there that when you complete the circuit, you have a loop of wire connecting both ends of the battery. The electrons will flow from one side of the battery through the device, and the device will consume some of the electrons. And then whatever's left continues to flow to the other end. I don't remember which one's positive, which one's negative without looking at the battery itself. So I'm not going to label which is positive or negative, but just know they come out of one part of the battery and they go to the other part. This is why if you ever stick a 9-volt battery to your tongue, it stings. That's because your tongue has saliva, which is salt water, and that salt water completes the current in the 9-volt battery, and you're literally, minorly, electrocuting your tongue. It's only 9 volts, so you know it doesn't hurt too terribly bad, but it sure don't feel nice. And no, don't make any younger siblings lick a 9-volt battery. It's not nice. It's not fun. Well, it might be fun for you, but it's not nice. So atoms are made of 3 parts. I know we haven't done atomic structure yet, so this is a little bit of a preview of atomic structure, which is unit 5A. So protons, yes, y'all are correct. They are positive. Protons are located in the nucleus. As well as the protons, we have the neutrons, which are neutral. They are also located in the nucleus. The protons and the neutrons don't move. They are stuck in that nucleus. So that solid blue area is my nucleus, and it has positive things and neutral things in it. The electrons live outside the nucleus in the clouds. The little red dots are my electrons. And depending on which model of the atom we use, we can visualize these electrons in a couple of different ways. So Bohr's atom is the one that we tend to use the most in physical science, and that's where the electrons are on rings. Technically, they're not. They don't go on a ring, but they do have energy levels, so that's kind of what the rings are representing. I'll make the dots a little bit big. Okay, maybe I shouldn't have made them that big. So Bohr's model, we show the electrons as little negative things on a specific energy level. Admit. Where's my, change the color back to black. So those little black circles are trying to represent different energy levels. Really and truly, the electrons are not in rings or on a ring. They don't travel in a circle. They really and truly exist in clouds that have three-dimensional shapes. It's like this is the shape of one type of clouds where the electrons could live. Each one of these little stuffed things is where we would find a different electron, and the nucleus would be really, really small in the middle. So it's hard to draw something like this, which is why physical science, we focus on Bohr's model. Now, most everything you encounter in your life is made of atoms. If it is matter, it is made of atoms. Few things that are not made of atoms. Heat and light, they're not made of atoms. They don't have protons, neutrons, and electrons. But yes, you can feel heat, you can see light, but most everything else you encounter is made out of atoms. So that model on the screen is Rutherford's model. It's showing each of the electrons in their own little orbital. But again, in the middle, in that nucleus is where we find the positive things and the neutral things. Neutrons are neutral, protons are positive, electrons are negative. It is bad to get hit by electricity. That's how I remember they are negative. Neutrons are neutral. They are not negative, they are neutral. Protons and neutrons have the same mass. In fact, they make up almost all of the mass of the atom. It takes about 2,000 protons. Bad misreadings. It takes about 2,000 electrons to equal one proton in terms of mass. So the electrons are nowhere nearly the size of the protons. They're much, much smaller. Not that you need to know that number. But we will eventually need to know where they are, where they're found, and their charges. So now, why are we even talking about this? Well, electricity. Electricity is the flow of electrons. We have electrons that are moving from one element to the other. When you are lighting up a lamp, there are electrons going from the outlet through the bulb back to the outlet. So the protons have the positive charge and the electrons have the negative charge. Those opposite charges cause an attraction. The negatively charged cloud, so the cloud is the cloud of electrons, is attracted to the positively charged nucleus. My negatively charged electron cloud is attracted to that positive nucleus. That is what holds my atom together. So I've got a positively charged nucleus and my cloud where all my electrons live, sort of, kind of in yellow. Oops. Can't see the yellow on the yellow. Is negatively charged. And they have a strong attraction to each other. For the most part, the number of protons equals the number of electrons. In neutral elements, the number of protons equals the number of electrons. So, for example, if I was picking on lithium, lithium has 3 protons and 3 electrons. So it is overall neutral. Lithium also happens to have specifically 4 neutrons. So my neutrons don't always equal my protons and electrons, but protons tend to equal electrons because most atoms are neutral. Now, if we happen to actually gain or lose electrons, that does produce a net charge. So yes, elements can gain and lose electrons, and when they do, they become positive or negative. If we gain electrons, we have went out and we have stolen electrons, we get a negative charge. If we have lost electrons, we get a positive charge. Not that we need to know that at this exact point in time. But if we have an excess or shortage of electrons, the element will have a overall net charge. So I'm going to pick on lithium one more time. Lithium likes to lose 1 electron. It always, when it forms a compound, loses 1 electron. So lithium always forms a -1 ion. And that's because it lost one of its electrons. And we have, Miss Rainey, it's not -1, +1, because we have more positive things than we have negative things. So you can kind of see neutral lithium, they're equal. Lithium ion, they're not. So Juan, I don't think I updated your attendance. I'm fairly confident I did not. Nope, I did not. Austin, welcome to class, sir. Alrighty, so protons and electrons have a property that we call an electric charge. In an atom, they have equal number of positives and negatives, so they are neutral. They end up canceling out. But we can have electrons flow from one atom to another. That movement of electrons is called electric current. So we only have electric current when the electrons move. Having a battery sitting on my counter, I'm not going to have electrons moving. They're just going to sit there. They're going to be potentially able to move. But electric current is the actual movement of electrons. Austin and Dewan, you're going to want to make certain that you are taking notes. I would pick up on the guided notes where we are currently. I think this week, today's is a Google slide. If you're using the guided notes, and I don't know what slide we're on specifically, but I know we should be fairly close to slide number, I added 3, so 10-ish. Okay. So different see, I changed it so that the presentation was taking up the whole slide, but I didn't realize that my line was going to be stupid. There we go. Okay, so we have an element. The element that we are playing with has 5 protons and 5 electrons. So notice up here in this box, there is no overall net charge. This thing is neutral. But if that neutral atom went out and lost an electron, we lose an electron. I'm erasing that last electron. We now have a positive net charge. So all of the elements who lose electrons become positive. It is positive to give. But if instead of losing that electron, we went out and we gained an extra electron, so that's me adding in an extra negative thing. That extra negative thing, we have stolen an electron. We are now negative. So the electrons who go out and they steal electrons become negative. Negative ions are called anions. Elements with a positive charge are called cation ions. They are cation ions because they are positively perfect. No, they really are called cation ions, but they only get that charge by gaining or losing electrons. We can't touch the protons. The protons are stuck in the nucleus. They don't move. They don't do anything. It's just these electrons that move around. So we are going to do fairly quick exploration. This is going to be fun. I got to change how I'm sharing, and I don't think I've actually got that simulation open yet. Got the other two. Madness reigns. So notice one thing I like about this simulation is it forces the elements, the subatomic particles to go where they're supposed to be. So notice if I try and drop a neutron on the rings, it won't let me. I can only bring it to the middle. The other thing that I like is it tells me what element I've made. So like right now, I've got 1 proton, I've made hydrogen. I got 2 protons, I made a version of helium. So it tells me which element I have. Additionally, notice we have no electrons. So if I expand this little plus sign, we can see that, hey, right now, this helium atom has a +2 charge. So notice that when I add my electrons, the first ones, it doesn't matter where I drop them, the first 2 always go to that first ring. That first energy level are where we put electrons to begin with. So now my positives equal my negatives. This thing is considered neutral. So earlier I was picking on lithium. Lithium has 3 protons, 4 neutrons, and 3 electrons. So right now, notice lithium has a positive charge because it has more protons. You can kind of see that up on the left. Oh, you know what? So got to get a better add-on. But anyway, in the top left-hand corner, you can see the total number of protons, neutrons, and electrons. So notice what happens when I add when I add 2 more electrons. So we now have lithium. If lithium had too many electrons, notice in this net charge area, I've got 1 more electron than I do protons. Therefore, it is a negative charge. I just noticed this. So I'm just curious. Oh, it just shows the cloud getting bigger. It doesn't actually show how many are in there. Oh, that's cool. Didn't know it did that. So that's kind of what we mean by the cloud. We don't actually see individual electrons, but this model is what we tend to use more with Bohr in physical science. Now, if I were to click the stable, unstable, we would see that apparently this lithium is stable. But if I take some neutrons out, there we go, that lithium is unstable. What that means is it would, if it really existed, it would decay. It would turn into something else. So that's what we mean when we talk about radioactivity. That thing would break down into probably a hydrogen and a helium. Or maybe 2 hydrogens because there's only 2 protons. So you'll have some time later in the period, but you are welcome to play with the same simulation. We will see it again when we get to matter. So I'm going to pick back up with my electricity. So electric force is a force of attraction or repulsion between electrically charged objects. The force of attraction or repulsion, the force of attraction or repulsion is proportional to the charge. What that means is if the charge goes up, so if we have an increase in charge, if my charge gets larger, then the force of attraction or repulsion increases the same. So if I had a +2 and a +2, with those both being positive, they're going to push away from each other. That's going to be a stronger force of repulsion than a +1 and a +1. They still repel, but they don't repel as strongly because they're not as large of a charge. Same thing with the attraction. If I have a +1 and a -1, these are going to attract. They're going to come together. But a larger charge is going to have a larger, I wrote those too close together, but they're going to have a stronger force of attraction. It is proportional to the charge. So if the charge increases, the force increases. The electric force is inversely proportional, so opposite, to the square of the distance. The whole thing didn't show up. Dang it. All right, make that a little smaller. There we go. So it is inversely proportional to the square of the distance. Basically, it's an exponential increase or decrease. Make that go bye-bye. There we go. So if I have charges close together, versus charges that are further apart. So these have a very, very small attraction because they are further apart. It technically is 1 over d squared, where the top two have a larger attraction because they are closer together. It's still 1 over d squared. It's just the force is stronger because the charges are closer. So, for example, if I double the charge, I double the force. So going from a 1 charge to a 2 charge would literally double the amount of force. But if I double the distance, I quadruple. It's 1/4 as strong. Wait, quadruple? Yeah, quad is 4. It's 1/4 as strong. Because it's 1 over d squared. So 1 over 4. It is 1/4 as strong. I doubled the distance. I went from 1 meter to 2 meters. That force at 2 meters is 1/4 the strength of force at 1 meter. Now, we are only talking about the forces of attraction within an atom. Dang it. These attractions are outside that atom are basically pointless. They're not strong enough. They do not overcome the force of gravity. So, static electricity. I'm sure everybody has done this, either slid their feet in socks on carpets or maybe pushed a balloon against their hair. But static electricity is the buildup of charge. When you're rubbing your feet on the carpet, you are taking electrons from the carpet and you are storing them in your body. The protons don't move, only the electrons move. And static electricity, that charges will build up and they don't flow until you close the circuit. So again, I'm dragging my feet on the carpet. I'm a little kid running around with my little onesies on, and then I go up and I touch mom or dad. And that's when that electricity transfers and flows from me to mom or dad. You shock yourself, shock your parents, shock your sibling when the electrons start to move. But it's the electrons that are building up, not protons. Protons don't move. Yes, same idea when you're going down a slide and it shocks you. Or if you go down a slide and your hair gets all staticky, same idea. You have you've gathered electrons from the plastic slide and you're building them up in your body. And when you touch something that's not plastic, you're going to transfer those charges. It was really fun back when slides used to be metal. You could like completely shock yourself several times going down the slide. Much harder now that everything's plastic or rubber. But you get off that slide and you touch somebody, yeah, you're probably going to shock them. especially if it's really, really dry out. So humidity kind of decreases it, but we have some really, really non-humid days. So there are 3 rules that electrically charged objects must obey. These 3 rules are: Rule 1, the law of conservation of charge. As we have seen other laws of conservation, when we say something is conserved, we're saying it does not change. So the law of conservation of charge says that the charge has to be transferred. It cannot be created or destroyed. It is only transferred. Going down the slide, I am stealing the electrons from the slide. I now have a negative charge because I have transferred those electrons from the slide to me. So this particular example, not everybody can do this. I can only get this to work when my hair is like freshly washed and dried. If you've got really, really thin, fine hair, it works really, really well. But this person rubbed both the balloons on their hair. And basically they were transferring electrons, depending on what the balloons were made of, they probably transferred from the balloons to them. Well, notice when they remove their head from the balloons that are now both positively charged are going to repel each other. But the balloon that has a positive charge is going to be attracted to his head because his head has a negative charge, or hair. We didn't just create the charge. We literally caused them to transfer by rubbing the object against something else. So conservation of charge. Charge cannot be created or destroyed. It is only transferred. Second rule that charges must fall. Oh, apparently I got ahead of myself. Not the second rule. Rule 1, second version. So when an object becomes charged, the electric charge is neither created nor destroyed. It just came from somewhere else. Static electricity is an imbalance in the amount of positive and negative charges. So this person, before they came up to the doorknob, had a lot of electrons in their body for some reason. And once they got close enough to that metal object, the electrons moved from them to the doorknob. You can see it, you can feel it, the electricity transferred. There was an imbalance of charge, and it eventually stabilized. Now, it only works under really small distances. Remember, the larger the distance, the less force there is. All right, rule 2, opposites attract. You've heard that in terms of relationships. Well, it comes from science. Opposites attract. If I have 2 opposite charges, they are going to be attracted to each other. My positive charge is attracted to the negative charge. But if I have 2 charges that are the same, they are going to repel. They are going to push away. Like repels, opposites attract. Again, the larger the charge, the greater the force of attraction or repulsion. But opposites attract and like charges repel. And rule 3, surrounding every electric charge is an electric field. You may not realize that it's there, but I promise around every single proton and every single electron is an electric field. I love this particular graphic because it actually shows you how the field lines line up. We can see that the positive in a thing has got the field lines coming out and the negative has them coming in. So in terms of which way the electric fields are going to go, we always go out from positive, positive out, negative in. I think I have a little lovely graphic. Oh, I guess I apparently don't. So the positive fields go out, the negative come in. So kind of using the words to remember. So an electric field is a region of space around the charge where we can feel that force. An electric field is the region of space around the charge where we can feel that force. So notice, I'm going to go back to the previous image for just a second. Notice we've got a lot of lines really close together when we are near the element, near the thing. That is why the force is really, really strong. The further away we get, the further apart the forces get, which is why we see a considerable decrease in the force of attraction the further we get apart. It is, again, technically 1 over the square of the distance. But you can see in this visual the reason why. The field lines are way far apart. It's going to be harder for us to feel that attraction or that repulsion because there's not as many. Versus if I'm right on top of it, I'm going to feel that attraction or that repulsion. Now, electric fields do not only exist around electric charges, they can also be created by moving magnetic fields. So we have electric fields just by the sheer nature of an electric charge, but if I move a magnet, I can create an electric field. If I move electrons, I create a magnetic field. And we will see that relationship a lot in this unit. Electricity and magnetism are very, very strongly related. I can use one to make the other. I think this is the last time I say it, but the strength of the field depends upon the amount of the charge. Again, directly proportional. When one goes up, the other one goes up. And the distance. That was that inversely proportional. When one goes up, the other one goes down. And it just happens to go down by an exponential rate. Oh, there's my pretty graphic. See, I knew I had it somewhere. It just wasn't where I thought it was. Oh, come on, technology. So positive, the field lines point out. Negative, the field lines point in. So there is another simulation. Yeah, I'm fairly confident this one is linked within the assignment because we have to use it for part of the assignment. Where is my, there it is. That is this one. So with this simulation, you want to turn everything on when you go to play with it. Because with it off, you don't actually see a lot of the really cool stuff. I'm going to also turn on my voltage meter. This is something that actually allows us to see the flow of electrons. And we'll put a couple sensors out here. So right now there are no electrons or protons or nothing. So there's nothing for them to really detect. But notice when I start putting charges out here that, oh, all of a sudden I got all these arrows. And if I move the charge, it changes the way the arrows go. So not only does it change the way those individual field lines go, but it also changes the way the arrows go in my little sensors. They're indicating the way the charge is attracted or repulsed. I'm going to put a second one here and a third one. Notice that area is getting larger and each of my voltages are getting stronger. Move this out of the way for just a second. So if I bring a negative thing over here, we can actually see the lines, the field lines start to line up. That's the attractive force between those opposite charges. So according to this simulation, that positive is going to get moved towards the negative. Really and truly, it's the electron that ends up getting moved toward the protons. But the neat thing, I'm going to grab and add another electron here. Notice when I have two electrons in the same area, let's turn that off. No, not that. Let's turn this off. Okay, we're just going to move them then. Notice how these arrows for these two negative things on the right side are pushing away from each other. That's that repulsion. We see the same thing if I take positive charges and I put them near each other. These arrows are pushing away from each other. We have a very strong force of repulsion the closer we get to those charges. The further away, the smaller that force. And we see the same thing over here. The closer I get to the two charges, the bigger that force gets. And just by changing the amount of charge, I'm changing the amount of force. And because I can't remember how to just delete them, moving them caused the arrow to spin around. Oh, there we go. There's the reset button. Oh, that's not good, Tanner. So good news is we won't have to really do the calculations for these individual charges. That's something that's beyond the scope of this course. That's more of a physics concept than physical science. Our calculations are limited to Ohm's law, which is kind of nice. Okay. 2, 3. There we go. Okay, so the last thing that electrical charges have to follow, the last rule that they have to follow, rule number 4, is that the electrons are going to move easily through a conductor. Electrons move easily through conductors. Conductors are things that allow heat and or electricity to move easily. Metals are the best conductors around. Metals are the ideal conductors. In terms of electricity, the best electrical conductor are silver, gold, and copper. But any metal can conduct electricity. So like we can run electricity through aluminum foil. It just doesn't do it as good as copper and gold. Now, electrons flow easily through conductors, but they don't flow easily through an insulator. Now, the reason they flow easily through a conductor is because of these electrons not being very tightly bound. The electrons in metals are free to move more easily than electrons in nonmetals. That's what makes metals our conductors. Conductors allow charges to flow easily, and the electrons are moved. Can move from one atom to another. Versus an insulator, they are things that do not conduct electricity well. So air is actually a pretty decent insulator. It does not conduct heat or electricity very well. But think about the things that we use on our chargers around the house. So every charger you've probably encountered is covered with plastic or rubber. That's because that is an insulator. It is protecting you from the metal inside that the electricity is flowing through. Insulators are things that resist the flow of electrons, and it's because they hold their electrons much tighter. They do not allow their electrons to transfer from one atom to another. So plastic, rubber, glass, those are all really, really good insulators. But things just as simple as cloth. The cloth is fairly decent at insulating. Now, there is a such thing as a semiconductor. A semiconductor are metalloids, tend to be semiconductors. There are carbon alloys that are semiconductors, and a semiconductor is something that under certain conditions can conduct electricity, but under other conditions don't conduct electricity very well. So silicon is probably one of the best examples. You get silicon really, really cool or fairly cool. It conducts electricity great. It's awesome. It's fabulous. But if silicon gets too hot, it stops conducting the electricity well. This is why your phone does not like to run when it is overheating. This is why your computer does not like to run when it is overheating. The silicon that are in the circuits can't conduct the electricity. It has gotten too hot, and the electrons are not flowing the way that they should. So that is just called a semiconductor. We don't get to play with them too terribly much, but they are an important feature of all the stuff that we encounter in our life now. I think that was where I was supposed to stop. I don't think I'm supposed to do transferring charge. Am I supposed to do transferring charge? Yes, I am supposed to do transferring charge. Sorry. So, types of electricity. There's two major types of electricity. You have your electric current. Plugging something into a wall is an electric current, but you also have static electricity. And there is a whole area of science where all they've done is study a static electricity and how it transfers and what allows it to transfer well and what does not. When we're talking about static electricity, there's generally 3 ways that you can get a charge to transfer. One of them I've already mentioned. So sliding my feet on the carpet. If you are sliding your feet on the carpet, that is transferring charge by friction. You're literally rubbing the electrons off of one object onto another, sliding down the slide. Your butt is rubbing the electrons off of the plastic side. So that is one way that you can transfer charge, literally by touching the object and rubbing it against the other. So not just touching, it's literally got to rub. So I had to, in order to get that kid's hair to stand on end, they had to rub the balloon against the hair to transfer the electrons from the balloon to the hair. Charge transfers by friction. This is me sliding my feet on the carpet. I am building up the charge by sliding it on the carpet through friction. But this right here is charge transfer by induction. The person's not touching the handle yet, but there is a charge that will jump from them to the handle. They didn't rub against it. They didn't touch it. We call that induction. And I think it's the third one on here, but this picture doesn't show them rubbing the carpet. The friction is literally the person who has rubbed their feet against the carpet. That is the friction. So the second way is contact. That's by touching. This is a Van de Graaff machine. AAS has one that works so-so. But if you've got somebody with fine, thin hair, they can literally get their hair to stand on end. There's a belt in there that's rubbing up against something else that's generating lots of charges really fast. But they only get it to work because they actually touched it. Kind of like, I think it still has batteries in it. So this, I can get the electrons that are being generated to go to my finger when I touch it. So that charge is transferring to my finger because I'm literally touching the plastic thing. So Van de Graaff is the big metal thing in the screen. This is an ion generator. So the third, as I said, was induction. Induction involves without touching. It is literally charges that are jumping from one place to another, and kind of sort of see it. Needs a darker background. Oh, that doesn't help. Darker still. Oh, that helps a little. You can kind of sort of see induction. Those little pulses that are in there is charges jumping from that center stem to the outer edge. I'm not doing anything to it. It's just doing it on its own. Not touching. I love that little toy. So friction is rubbing together. Charge transferring by conduction is touching. And induction is not touching. Another good example of induction is if you happen to have ever been struck by lightning or know somebody who's been struck by lightning. That lightning came, oh, it's because you were near a tree, came through the ground and you just happened to get zapped by it because you were near the object that was struck. It also could go through the ground and come up through your feet because your feet were touching the ground. All right, so last simulation is the balloon one, and that is this one. And this is the next best thing. So it's kind of cool. I want it to show, no, I want it to show charges. Actually, I want it to show charge difference. So notice, yeah, right now, nothing has charges. I'll come over and I'm going to put my balloon against the shirt. So we are transferring electrons from the shirt to the balloon. And now that balloon wants to be attracted to the shirt. It's not attracted to the other balloon because it doesn't have any kind of charges. I should. Oh, it's not going to let me do that. So now not only are the two balloons attracted to the shirt, but and the wall, but they don't like to be near each other. Although, unfortunately, the simulation has a small flaw where it will let them both be on the wall. If I change the material of the shirt, instead of the shirt losing electrons, it could steal the electrons from the balloons. It all depends upon the materials. So rubber is really, really good at accepting and donating electrons. It can go either way. Latex can do that. So like if I'm rubbing it against my hair, I'm transferring the electrons from the balloon to my hair. But since I'm rubbing it against the shirt, it's kind of the opposite. Reset balloons. Show all charges. There we go. That's what I wanted to do earlier. There we go. So notice as I bring this balloon close to the wall, through induction, it is pushing those electrons away the balloon. And it will cause the balloon to stick to the wall because we now have negative and positive things. But it literally changes the position of the objects in the wall. Technically, it's not supposed to be attracted to the wall, but I won't ask why I just did that. But you can kind of see as I add more electrons to the balloon, we have a greater change in the electrons in the wall. And that's what causes the balloon to stick to the wall. It's that attraction between the positive things that are left when the electrons are induced to be further away.